do a rotation, which I'm saying is like that, which takes you into the B position. If you start in the A position again, you can flip sideways, which takes you into the C position. And if you flop, I'm calling that flop this way, then you get into the D position. So if you do each of those things and then do nothing afterwards, you get the same answer because it doesn't really matter when you do nothing. You can do it anytime you want. How about if you do a rotation followed by a rotation? So if you do a rotation and then you do another rotation, you get back in the A position. If you do a flip and then another flip, you also get back in the A position. And of course, if you do a flop and then another flop, you also get back in the A position, which shows you can't keep doing the same thing every season because you'll always keep ending back in the A position and you'll always have skipped some places. So now we have to combine something. Well, we don't have to, but we can. So we can try doing a rotation and then a flip, which takes us to D. We can try doing a rotation and then a flop. So if you do a rotation and then the flop, that takes us to C. And if we do a flip and then a rotation, a flip and then a rotation, we get D. And then maybe you start seeing a pattern, which is how a lot of maths research goes. You want to save yourself some work, so you spot a pattern and then try and justify it after the event, which is often easier than justifying it before spotting the pattern. So what do you think goes here? B. And what do you think goes here? C. And what do you think goes here? B. So if we are good mathematicians, we should probably check that. But I'm going to tell you it works. And then the question is, how many Battenberg cakes can you see in that picture? So there's these ones. There's also those ones. There's one in the middle, but there's my favorite one, which is the fact that the whole thing is a giant Battenberg cake, each of whose cakes was already a Battenberg cake. So here's that. It's an iterated Battenberg cake. And I call it the iterated Battenberg cake because what I've done is I've iterated the process of Battenbergification. Battenbergification says I'm going to take a grid and I'm going to paint like numbers. So all I have to do is tell you what's going to go in position 1 and in position 2. So it could be yellow and pink. Or it could be chocolate and more chocolate. It could be a bunny and another bunny. Now I've Battenbergified a bunny. Or it could be one type of Battenberg cake and another type of Battenberg cake, in which case I get the iterated Battenberg cake. And this is quite an advanced piece of abstract maths that you usually only see if you're a second-year undergraduate maths student. So I say, why not show it to everyone anyway, because it's kind of cool. And here is a very abstract representation of Battenberg cake. So all I had to tell you actually was 2 pieces of information, what goes in position 1 and position 2. So it could be yellow and pink, it could be chocolate and more chocolate, it could be bunny 1, bunny 2, or it could be cake 1 and cake 2. But what is cake 1? Cake 1 is already one of these. And cake 2 is already one of those, so why don't I put those over there where it says 1, and put cake 2 over there in the second position. And this gives me an extremely abstract representation of an iterated Battenberg cake, where I've basically removed all the information apart from what I'm putting in. And so this is now a tree. It's what mathematicians study, and they call them trees. And trees come from sticking things together, because